Okay, let's do some of the two-way ANOVA classwork problems. And again, you know what I believe at this point, and that is that with the examples here, I think it'll start to click. We're going to do two without interaction and one with interaction so you can see the difference. Okay, first problem here. Greenville wishes to study the driving times of taxi drivers on various routes. Using the 5% significance level, do taxi driving times vary between driver or route? Test the factor means and discuss the breakdown and variation. All right, so let's write the hypothesis test first. So the first one we're going to have is a hypothesis test for driver. So we're going to have a null that says all driver means are equal, and an alternative that says at least one driver mean unequal. And then we have our route factor of all route means equal and I don't know what I'm thinking here. Let's see here. And our alternative of at least one route mean unequal. Okay. What are the p-values? So really to answer everything else, we need to go over to JASP. All right, let's take a look at our data first. Here's our driver. All right, notice here I create a lot of this data, and these are all last names from famous horror movies. And we have some routes from Greenville, and we have some travel time. All right, so we want to go to ANOVA. All right, travel time is our continuous variable, so that's the dependent variable. Driver is one of our fixed factors, and route is the other one. All right, aha. So do you notice here, like we've got a problem, right? There is an error, there is a problem. And let's go to model. All right, do not worry when this happens. So JASP automatically calculates an interaction term. And we do not have replication in this data set. We cannot test interaction. So we've got a problem where we need to highlight driver times route and remove it from the model. And you see now we get an actual ANOVA table. All right, assumption checks. Let's do homogeneity for our variances. And it cannot calculate. And we've got... Let's see here. We can do post hoc tests on our individuals, and let's see, check Bonferroni here. And descriptive plots. All right, let's put route on the horizontal axis and put driver on separate lines. All right, let's not do error bars for this. It might get a little bit difficult to see. All right, let's see here. Anything additional? Yes, under additional, let's do estimates of effect size. All right, so I'm trying to think of everything that I could possibly ask you for. All right, are we good? All right, so let's split our screen here, and I'm going to open this so we can, there we go, we can see everything. Okay, so what are the p-values? So we've got a driver p-value, and the driver p-value, we can look in our ANOVA table here, and driver is less than 0.0001, and our route p-value equals 0.004. All right, we see these p-values in our table. So what are the decisions for driver? The decision is reject the null. And for route, our decision is reject the null. All right. And what are our conclusions for driver? At least one driver mean is, I should say, at least one driver driving time mean is unequal or different. And for route, at least one route driving time mean is unequal or different. All right, discuss the breakdown and variation. All right, so this is where we look at our eta squareds here. So we've got 52.2% of the total variation in drive time is explained by driver. All right, and look at our eta squared for route, and we get 0.318, so 31.8% of the total let's try this again. Variation in drive time is explained by route. All right. If we add these up, notice that they sum to 83 point, actually it looks like 84%. They sum to 84%. All right, so what that means is that 16% of the total variation in drive time is unexplained. Okay, let's keep looking at this though. So we can look at our post hoc test. So notice here we can get two-way comparisons between our drivers. So I could ask you, do Blair and Torrance significantly differ? And we could look at Blair and Torrance and see a p-value of 0.011. So Blair and Torrance do significantly differ. We see here that Kruger and Torrance with a p-value of 0.939 do not significantly differ. The same for routes. We can see that East North Street and I-385 have a p-value of 0.081, so they do not significantly differ on mean drive times. All right, and so here's a plot that just looks like a big hot mess, but just I wanted you to see how you could plot both of these on a single graph. It's not going to be as important until we actually have our interaction data available to us. All right, let's go to the next problem. You work for a shampoo company and wish to better understand if there's a trend to shampoo sales. In the data, you have shampoo bottle sales in millions of dollars for the summer months by hair type. Using the 5% level of significance, do shampoo sales significantly differ among months or hair type? Test the factor means and discuss the breakdown and variation. All right, so it looks like here we have months. Well, it's important to spell months, and we've got a null that says all month means are equal, and an alternative, at least 1 month mean is unequal. And then we've also got hair type and a null that says all hair type means are equal, and an alternative that says at least 1 hair type mean is unequal. All right, so let's just take a look at our data first before we dive right in. So we can scroll over, we see here we've got month, we've got the shampoo type, and the sales. So how do I know we do not have the ability to test for interaction? Notice that for the combination June and dry hair type, we have 1 sales amount. We do not see any other June dries. There's only 1. Therefore, there's not replication of each factor by factor crossing. And we see that's true. For each month and each hair type, we have only 1 observation. Okay, so let's go into ANOVA, and we've got sales as our dependent variable and month and shampoo as our fixed factors. And again, we're seeing this big error. Something's wrong, and that is that we need to remove the interaction. All right, let's go into post hoc and move them both over. All right, and make sure you check Bonferroni since that's what we're teaching here. All right, let's go under additional options and check our estimates of effect size. All right, and I think that's good for right now. All right, so let's look at our ANOVA. All right, what are our p-values? So for month, the p-value equals 0.240. And for hair type, the p-value equals 0.690. All right, notice both of these p-values are bigger than 5%. So for month, we fail to reject the null. And for hair type, we fail to reject the null. All right, what are our conclusions? Well, for month, there is not enough, there is not enough evidence to conclude a difference, so there is not enough evidence to conclude at least 1 month mean is different. And for hair type, same thing, there is not enough evidence to conclude at least 1 hair type mean is different. In other words, okay, let's put this in layman's terms. In other words, shampoo cells don't significantly differ across months, and shampoo cells do not significantly differ across hair type. Okay? Does this make sense to you? Yeah, it should make common sense, right? Because we think of shampoo as something that is inelastic, like demand doesn't really vary. You don't go through phases where you wash your hair a lot and then you don't wash your hair for a month or two. All right, so you're pretty consistent on how much you wash your hair, and I think most people are probably like that. All right, let's discuss the breakdown and variation. So what we should see here, since we do not have significant p-values, is that we should see that not a lot of the variation is really explained by these factors. All right, so if we look at month, we have 43.8% of the total variation in shampoo sales is explained by month. All right, and then with hair type, we get 5% of the total variation in shampoo sales is explained by hair type. All right, so students often ask, well, when is it a lot of a percent? And the answer really goes back to the p-value. The fact that month's p-value is 0.24, it's not significant, we would interpret 43.8% as not very much of the variation in shampoo sales. Something else is doing a better job. All right, and then just looking at these post hoc tests, there's really no reason to look at them because we do not have significant p-values here in the ANOVA table. So really, if I were rerunning this, I would uncheck post hoc because these p-values in the ANOVA table are greater than 5%. All right, let's take a look at our interaction problem. Greenville again wishes to study the driving time of taxi drivers on various routes. Now we have sample data, 3 observations for each driver on each route. Using the 5% significance level, do taxi driving times vary between driver or route or an interaction of the two? All right, interpret an interaction plot before proceeding with the ANOVA. All right, do an interaction plot, and discuss potential interaction. All right, so if we scroll over in our data, we see now let's look at this. We have Blair, I-385, and for that combination of factors, we have our 3 observations. We have 18, 15, and 21. So we have that replication or sampling of each factor by factor crossing. All right, we cannot in JASP just do an interaction plot without doing an ANOVA. So let's go ahead and do everything, but we'll start by talking about the interaction plot. So let's do an ANOVA, and we're going to put that last driving time in the dependent variable, and then driver 1 and route 1 in the fixed factors. Now notice we don't get an error message because we can calculate the interaction. All right, so we see our interaction here in the model, and we want to leave it there. All right, let's go to descriptive plots. Let's put route on the horizontal axis and driver on the separate line. It doesn't matter. Typically, the one that goes on the separate line is the one you think of being the moderator, the one that is changing the direction of the other thing, right? And I see driver as more variable than route. Route's not really going to change a whole lot. All right, no need for error bars here, but let's make sure we go under additional options and get our eta squareds or our effect size. Okay, so let's start with our plot. So scroll down. And notice here that they're all crossing, right? Nothing is parallel. So I'm going to say here with the plot, since lines are crossing, there appears to be significant interaction. All right, there appears to be. We don't know yet because we haven't looked at the p-value. Okay, this is just what we are thinking right now. All right, let's write our hypothesis test. So we've got the interaction, our null, there is no interaction between driver and route, and our alternative, there is interaction between driver and route. All right. We've got our factor mean of driver. So that null is going to look like all driver means are equal, and an alternative of at least one driver mean unequal. And we've got route here of all route means are equal, and an alternative of at least one route mean unequal. All right, what are the p-values? So for our interaction, we're going to have one. For our driver, we're going to have one. And for our route, we're going to have one. All right, let's go to our ANOVA table in JASP. And for the interaction, this is driver 1 times route 1. And we scroll over, and we see a p-value of 0.046. For driver, we see a p-value of less than 0.001. And for route, we see a p-value of less than 0.001. All right, what are our decisions? Well, for the interaction, our decision is reject the null. For the driver, our decision is reject the null. And for our route, our decision is reject the null. Real quick here, notice though, we're using a 5% significance level or a 5% alpha. Notice if we had been using a 1% alpha, we would not have rejected the null for interaction. So it's only because we're using a 5% alpha that the interaction is actually significant. All right, remember, that means we've got a 4.6 chance of making a wrong decision, or a type 1 error. So sometimes we like to see smaller p-values than that. All right, what are our conclusions? Well, for interaction, there is significant interaction between driver and route. For driver, at least one driver mean is significantly different. And for route, at least one route mean is significantly different. All right. Discuss the breakdown and variation. So this is where we look at our eta squareds. And notice now we've got 3 eta squareds. We've got an effect size for each of our factors as well as our interaction. So we've got 38% of the total variation in drive time is explained by driver. I'm not sure what I did there, variation. All right, we've got 26.4% of the total variation in drive time is explained by route. All right, and then 13.5% of the total variation in drive time is explained by the interaction of driver and route. So again, what this is saying is that some drivers drive some routes differently. Okay, maybe Blair drives I-385 very quickly because it's the highway, but Blair drives Main Street particularly slowly because it is not a highway. Okay, so there's just an interaction between driver and route. All right, we could add these up, all right, and we are getting, all right, they sum to, let's see here, 14, 17, 77.9%, all right, so that is telling us that 22.1% of the total variation in drive time is unexplained, assuming I don't have a simple math mistake. All right, but that is an example of an interaction problem. And let's actually, while I am doing this, let's go back to post hoc test and go ahead and move driver and route over to our post hoc test. Check Bonferroni and uncheck Tukey. All right, let's just take a look at this. I'm going over this while I'm not specifically asking for it in the homework or the quiz. It is something I want you to be able to potentially do for your final project. And this is where, you know, we can really drill into those significant differences. So we found a driver, or at least I should say at least one driver that drives significantly different. Let's see here. Blair and Torrance. Blair and Torrance have a significant p-value, all right? Notice this mean difference is is negative. So what this is saying is that Torrance drives significantly slower, all right, than Blair. That's how we would interpret it. It's Blair minus Torrance. All right. Let's see here. Kruger and Warren. All right, Kruger and Warren has a significant p-value, and here we would say Kruger drives faster than Warren. Are there any routes that are particularly different? We see here that Haywood Road and Main Street are significantly different with the p-value of less than 0.001. This positive mean difference is saying that Haywood takes significantly longer than Main Street on average. All right, here I-385 is significantly quicker than Main Street. All right, is it significant? No, it is not. Look at this p-value, 0.304. So we cannot conclude that I-385 and Main Street are significantly different. All right, but again, while I'm not asking that specifically in the homework or quiz, this could be useful to you in doing more two-way comparisons from an ANOVA for that final project.